Now let's introduce the finite difference approach to calculating derivatives. A common manner to numerically estimate the derivative is called a finite difference of this quotient. The forward difference at x with step size h is denoted f prime f for forward, and it's f of x plus h minus f of x over h, where h is some fixed number. So it's the quotient of the normal derivative but without the limit. H is chosen fixed. The backward difference just goes backward, f of x minus h over h, again with a fixed step size h. In the limit, that would also be the derivative, but here it's a backward difference. The center difference goes forward h and backward h, and then of course divides by 2h, which is the run in that case. It's easy to calculate that the center difference is actually the average of the forward difference and the backward difference. Take 1/2 of each of those and add them together. The f of x's cancel, and you're left with the center difference formula. What I'd like to point out is in each of these formulas, there's no limit as h goes to 0. H is chosen to be a fixed positive number, and that results in these three different formulas that estimate the derivative. For all of these formulas, in the limit as h goes to 0, they all recover the actual derivative. Suppose the function values are only available as data pairs, x1, f of x1, x2, f of x2, up to xn, f of xn. Let's let yi denote f of xi. Then the finite differences are computed just with the data, and assuming the xi's are sorted, the forward difference at xi is yi plus 1 minus yi over xi plus 1 minus xi. The backward difference is similar, yi minus 1 over xi minus 1. These are all just the slopes of the lines connecting the points. In MATLAB, this is very easy. Take the y data and the x data and use the diff command, which creates those differences, and do an element by element divide. If the y data and x data are of length n, then this variable der est is of length n minus 1. Therefore, when we plot it, we need to be careful and only plot some of the x data. The forward formula is unable to compute the derivative estimate at the last point because there isn't a I plus 1. Similarly, the backward formula is unable to compute the derivative at the first point because there isn't an I minus 1. So notice the way I've plotted these, I've adjusted the x data depending on whether I'm plotting the forward or backward difference. Try that out. For the centered formula at xi, only the previous and next values of y and x are used. You can think about the MATLAB code that would implement that. Let's try this in MATLAB. Here I have a function e to the negative x cosine of 2x. I can calculate the derivative of that myself. Here's the derivative as an anonymous function. Let's also produce data linearly spaced from 0 to 3 with 50 points, and then take the function value at that data. And we do the finite difference estimate using the diff command, diff of the y data, diff of the x data. And then for graphical purposes, I'll also have a much finer x data for plotting the exact values. On a subplot, we'll plot first the function. So the fine values of x and then f of the fine values of x. That'll be an oscillating sine wave. Below that, we'll correctly plot the forward difference in red circles, the backwards difference in blue pluses, and the exact derivative as a black line. We'll give it a legend, forward, backward, exact. Let's try that. The function is shown above, an oscillating cosine, and the derivative and their estimates are shown below. The black line is right down the middle. You can barely see it. And above it and below it, depending on where we are in the curve, are the forward estimates of the derivative and the backward estimates of the derivative. They're not exact, as you'd expect. Now let's compute the centered estimate. There's the expression right here, which involves y starting at point 3 to the end minus y starting at point 1 to the n minus 2, and a similar thing for x. So check that out. We'll just plot the center derivative estimate and the exact derivative. And then below, we'll compute the errors of each one. The errors of the forward taking the derivative estimate minus the exact derivative, the errors of the backward, taking the estimate minus the actual, and the errors of the centered estimate. We'll plot those in absolute value with red circles, blue pluses, and green stars. On the top, you see that the centered estimate is quite accurate, almost lying on the exact derivative, and the errors are shown below, which just confirm what we saw. The forward and backward schemes have some errors that are large in some cases, and the centered scheme's errors seem to be generally smaller. There's a 1 or 2 points where it's comparable, but generally the centered estimate errors are smaller. Let's do irregularly spaced data. Function's the same, but instead of creating linearly spaced data from 0 to 3, I'll create randomly spaced data from 0 to 3. So I'll use rand 1, 50 to make 50 values randomly spaced between 0 and 1, sort them to get them in the right order, and then multiply by 3. That'll give me a range of 0 to 3. Then follow the exact same procedure. Let's see what happens. The exact function is shown above, and below is the exact derivative as well as the forward and backward estimates. Fairly similar story to what we had seen. Now let's do the centered with the irregular data and the errors. Up above is the exact derivative along with the centered estimates. They're not as perfect as they were before. And down below are the errors. Notice that generally the centered errors are a little bit smaller, but things are a little more comparable. Typically the peaks are occurring with the blue pluses and the red circles, the forward and backward estimates, and the centereds are a little more accurate.